questions or concerns or needs, etc., before we get started?
What's your next test?
It was originally scheduled for April 8th, but I'm moving a few things around and it'll probably happen a week after that. Try to put a calendar up real quick. Visualize stuff.
So it's just that test and then the final, right?
Basically, yeah.
Okay.
Time and date. Spell time right. All right, let's see. On the syllabus, I originally said that test 2 would be around here, April 8th through 10th. However, just because, things always get taught at a slightly different rate than I expect, combined with the fact that that's Eclipse Day, and I want to do something special about that, I'm leaning towards rearranging things and moving test 2 to be this span of days, the 15th through the 17th. I never like making tests sooner, so instead I will make it later. Which would give us the tail end of that week and the following week to wrap everything up and get ready for the final. Sound fair?
Oh yeah.
Okay. So that's my current plan. I'll let you know if anything changes leading up to that point. Anything else on your minds? All right. In that case, let's talk about this week. We've been discussing matter and fluid pressure is the last thing we talked about. We're going to pick up where we left off last time and talk about why fluid pressure causes the phenomenon known as floating. So to review what we did on Friday, we went over the concept of fluid pressure, the idea that when you are submerged within a fluid that includes liquids and gases, because they both exhibit fluid tendencies. When you're submerged in a fluid, that fluid is going to exert pressure on you because that fluid's weight is going to bear down on you and press in on all of your sides. And that fluid pressure is equal to the density of the fluid times the strength of gravity on this planet, ignoring the negative sign, you just want the 10. And then also times the depth you are within that fluid. This is where air pressure comes from, because there's several miles of air above you, the weight of which is bearing down on you. It's also where water pressure comes from. The deeper you go in the water, the more water is above your head, the more water pressure you have to deal with. Does that all sound familiar? Any objections? Okay, now, our exercise for today is to discuss how this phenomenon links to the sensation of floating. Now, I'm personally pretty bad at floating myself if I'm in a pool, but various objects are capable of floating, so including and not limited to styrofoam or boats or wood, all things capable of floating in water. And today I'm going to explain to you the secret reason why that happens and how it is tied into fluid pressure. Any questions or objections before moving on? All right. Now, there is a force responsible for making things float, and we call that the buoyant force, spelled B-U-O-Y-A-N-T force, which is a specific term for floating. And it's the same root word as in buoy, the things in the ocean that float, buoys, buoyant, so it all just means floating. And there's a force that's responsible for making things float, which kind of makes sense because if you are not, say, submerged in water, if you're just falling, there's a force of gravity pulling you downwards. And you don't escape that when you enter the water. That doesn't go away because that's a function of Earth's core, and the water doesn't know anything about the core of the planet. So, weight doesn't go away. In order to float, you have to apply some amount of upward force to counteract that force downwards, which is basically the exact same thing as when something is sitting on a flat surface and normal force keeps it from falling through the table. Normal force acts up, cancels out with gravity down, and you remain in place. Floating is technically the same thing, except there's no solid surface supporting you. Instead, the fluid you're floating in provides a buoyant force instead of a normal force. The names change because it's a slightly different phenomenon, but it still causes the same net effect. In order to float, there has to be a buoyant force up, canceling out the force of gravity downwards. If the buoyant force is not strong enough to counteract gravity downwards, you sink. Does that make sense? All right. Now, why does buoyant force happen? Where does it physically come from? To have buoyant force, first you have to be submerged in a fluid. So I'm going to take this cube and I'm going to put it underwater. So the water is going to be our fluid for right now. And because that cube is now in water, that water is going to exert water pressure upon the cube, as we've discussed. Now, a couple things to know about pressure. One, the official definition of pressure is force over area. And that means that the water pressure acting on this cube is going to exert force on all of its flat surface areas. And I'm using a cube because all of its faces are flat. And therefore it should be easy to visualize what direction those forces are going to point. The thing about fluid pressure is it always acts perpendicularly into or out of the surface it is acting upon. It always perpendicular. If a face is horizontal, perpendicular will be either up or down. If a face is vertical, perpendicular will be either left or right. And fluid pressure always points away from itself. Fluids, be it either liquid or gas, point away from themselves and act upon whatever they're acting on. So on this cube, on all of its flat surface areas, all of the force arrows that we are going to draw should point into the cube's surfaces, perpendicularly into the cube's flat surfaces. Because the force is always going to go from the water into whatever it's acting on. And since all these cube faces are flat, all of the arrows should point either inward horizontally on the vertical surfaces or inward vertically on all of the horizontal surfaces. So I'm using a cube for simplicity's sake. The water pressure is going to exert force on all of this cube's surface areas. Does that sound okay so far? All right. Now, that's part of where the buoyant force comes from. The pressure is going to exert force on the cube's surfaces, and that's already part of the buoyant force, the fact that the pressure creates force on the area of the cube. The other part of buoyant force that's important to know is, does the force on this cube, does the pressure on this cube stay constant on every single part of the cube? Or rather, let me ask it a different way. Does water pressure stay constant as you go deeper into the water? No, we've already discussed, based on this formula, fluid pressure increases with depth. So the deeper into a fluid you go, the more fluid pressure there is. The deeper into the ocean you go, the greater the water pressure gets. And that means that, technically speaking, the pressure is greater on the lower part of the cube than it is on the upper part of the cube. Maybe not by a lot. Like, the water pressure is not going to increase super dramatically, just from here to here, if we're taking these distances literally. But it's still technically bigger, and that technicality is going to be important. Technically, the water pressure is bigger down here than it is up here. And that actually means that the force arrows on the lower part of the cube are going to be bigger than the force arrows on the upper part of the cube, because more pressure down here means more force on the relevant surface area of the cube. Does that make sense so far? Okay, so the pressure is going to exert force on the cube's surface areas, and that pressure, and therefore the force, is going to be bigger on the lower parts of the object. These two things are starting to form together into what causes buoyant force. I'm now going to start drawing force arrows all over this cube to represent the force from the water pressure. And I'm going to start with the two left and right facing sides. On this left side, the pressure is constantly increasing the deeper you go. So the pressure is strongest on this part and weakest on this part. All the force arrows on that side have to point into the surface, perpendicularly into the flat of the cube, but because the pressure is bigger on the bottom, the force arrows will be biggest on the bottom part of that face. Does that make sense? Does that not make sense to anybody? Okay. So the deeper you go, the greater the force from the water pressure. More pressure, more force. There's a related phenomenon to this, something you might have seen before that I'd like to very briefly demonstrate or show you. Trying to find a picture that shows it. Bless you. Yeah, that'll work. Water pressure increases with depth, and that is why the Hoover Dam is shaped like it is. Most dams are, but I'm using the Hoover Dam as a main example. The Hoover Dam is curved. One side of it is flat, but the other side of it curves outward like this, and that's the side that's currently pictured here. It's physically thicker on the bottom. And that is for the same reason as the slide I just showed you. Water pressure increases with depth, meaning that on the other flat side of the dam where all the water is, the force arrows get bigger on the lower part of the dam, and that's physically why the bottom part has to be thicker to support the increased water pressure at the increased depth. So, I promise, I'm not making this part up, all right? Make sense? All right, now that's just one of the faces of this cube. I'm now gonna draw arrows on the right facing side, so this one here. And on this side, the same basic thing happens because, you know, as you scroll down this surface, the depth increases too. But inward on this side, points to the right, points to the left instead of the right. So all of those arrows are the same size as the ones on the other side, but they point in the opposite directions. So scrolling down, the arrows still add up to 0 on this particular cube. And that's why water pressure doesn't usually cause things to drift side to side by itself. The net horizontal force is still 0, and that's why you don't float left and right. You need a current for that. It's also why the Hoover Dam is built like this, because there's a lot of water pressure down here, but there's only air pressure on the other side canceling it out. If it was entirely underwater, not sure what that would accomplish, but if there was water on both sides, you could make it a straight line. But since it's air on this side, they had to reinforce it against the increased water pressure. But here, since both vertical faces are underwater, the force increases at the same rate down both sides, and the left and rights just cancel out. Does that sound all right? Okay, so that is why you don't float left and right. Now something different happens if we look at instead the top and bottom faces of this cube. And that's because the top and bottom faces are all at one solid depth, right? The entire top of this flat cube is at one constant depth. It doesn't dip up or down at any part. And that means that all the force arrows acting inward on the top of the cube are all going to be the same size. And inward on this top surface is going to point down. So all of those arrows are the same size as each other. And this technically means that an amount of the water pressure is just pushing straight down on the cube, which in my opinion makes sense because there's this much water above the cube physically trying to push it down with the weight of the water. So on that topmost surface, the force arrows point down into the flat surface of the cube. And the same basic thing does happen on the bottom of the cube, except two things. The bottom of the cube is deeper than the top, meaning that the force arrows underneath are actually going to be bigger than the ones up top, because more pressure means more force. And what direction does inward point on that bottom surface? Up. So the inward pointing arrows on the bottom surface point up, and they are bigger than the downward pointing arrows on top. So adding all of these force arrows together, what direction does the net force from the water pressure point? Up. Yeah, the left and right cancel out, and the upward is bigger than the downward. So the net force from the water pressure points upwards. And that is the buoyant force. So that's where it comes from. Literally, it's just the water pressure acting on all the surface areas, but slightly stronger upward on the bottom than down on the top. So that's where it comes from. Sound good? Makes sense? All right. Now this happens anytime you are submerged in any fluid. All fluids do this because pressure from any fluid increases with depth. So even if you're only half submerged in water, the pressure on your feet is still greater than the pressure on whatever point the water level comes up to. And therefore there is some buoyant force just because you are in water. Now, I have a hard time floating when I get in the pool, but technically speaking, since there's any buoyant force from the fluid, as soon as you enter the water, there's an added force upwards that isn't normally there, and that's why you should immediately feel lighter in the water. Does that sound right? It's because literally the buoyant force is pushing up, maybe not perfectly canceling out gravity if you don't float very well, but at the very least mitigating it. So by being in a fluid, there's some amount of buoyant force technically making you feel lighter than you normally would. And technically, the air does this too, because air is a fluid that's exerting pressure on our bodies, right? And our feet are at a deeper point in the atmosphere than the tops of our heads are. So technically, the air is currently exerting buoyant force on you. It's not a lot, because the air is not very dense at all, but it's technically there. You would feel heavier if the Earth had no atmosphere, because there'd be no buoyant force from the atmosphere technically making you feel lighter. Of course, if we had no atmosphere, we'd have other problems prior to that one. But it's interesting to think about. So, all fluids do this whenever you are submerged in that fluid. Questions? All right. Now, we call again this net force from the water pressure the buoyant force. And in order for something to float, the buoyant force generated has to cancel out the force of gravity downwards. If something is currently floating, it means these two arrows add up to 0. Again, basically the exact same as gravity and normal force canceling out if you're sitting still on a flat surface. So in order for something to float, buoyant force up and gravity down must cancel out. If buoyant force is weaker than the weight of the object, you sink. 1 Newton up versus 10 Newtons down, the net force is 9 Newtons down, you still sink. Whereas if buoyant force is stronger than gravity, you actually will rise. It is possible for buoyant force to be bigger than gravity, and that creates scenarios where the object rockets back up to the surface. Because if buoyant force is 10 and gravity is 1, net force is 9 upwards, you will rise until the buoyant force goes away when you leave the water. And that's the kind of situation you get when you take the whole beach ball and jam it under the surface of the pool. You let go of it, it shoots back upwards. So that's what I consider to be the rules for floating. If buoyant force is less than gravity, you sink. If buoyant force is greater than gravity, you rise. If buoyant force is equal to gravity, you stay where you are. Sound good for the rules for floating? All right. Now, in order to use those rules, we have to be able to calculate buoyant force. So I've got a new formula for you. This is the formula for buoyant force, and within physics, this formula has a name, that name being Archimedes' principle. Have you heard of Archimedes? Has heard the name before? It's okay if not, I'm just curious. We call this Archimedes' principle because it is named after a specific Greek scientist, philosopher, Archimedes. The legend goes that Archimedes' research that led to this equation happened one night when he was taking a bath and he noticed that the water level in the tub rose when he got into the tub. I will now demonstrate this with this iron weight as I add it to this beaker of water. Right now, I've drawn a red line where the water level in this beaker comes to. It's currently at about 500 milliliters. And I want you to notice what the water level changes to once I add this iron weight. So, note again, it starts there on the red line. I add the iron weight. And it increases to slightly over the 600 milliliter line. So, by adding that iron weight, the water level rose. Is there more water in the beaker? No. Why does the water level rise?
Volume of the object.
Volume of the object. The object itself has a volume of about 100 milliliters, and now it is taking up space in the beaker, and it shoved 100 milliliters of water out of the way. So, again, the legend goes Archimedes figured this out, and again, the legend also mentions that he used it to figure out the volume of a non-standard geometric shape. Question?
Yeah, like, let's just say that was an ice cube.
Mm-hmm.
If it melted, would it be that height or would it be lower?
That is a
makes
great
sense.
question. The thing about ice is ice floats.
Yes.
And the water level would only increase by the volume of ice under the water. So, to start with, if there's 1 milliliter of ice under the water level would rise by 1 milliliter. But as the ice melts, the water level might continue rising, because once all of it becomes water, all of it's going to be in the water.
Mm-hmm.
And then it's kind of hard to tell what was there and what just melted. But I'd say that the water level might technically rise slightly once the ice completely melts.
Okay.
Although this is it's an interesting scenario you've asked about, because ice is one of the few things in the known universe that gets bigger once it becomes solid. So technically, once it melts, the resulting puddle of water technically has less volume than the whole ice cube does. So it's kind of a mixed bag. Like, more of the object is now in the water, but the object takes up less space as water than it does as ice.
Yeah.
So it's a very complex situation. That's why you might not notice the water level change much as your beverage melts. Does that answer the question?
Yes.
Okay. So, that's why we call this formula Archimedes' principle. And you can use this trick to determine the volume of any shape, even if there's not a formula for it. The legend goes Archimedes used it to find the volume of a crown, and there's not a geometric formula for a volume of crown. So you can use this trick to find the volume of anything. Remember that for lab today or this week. But because of that whole tale, we call this formula Archimedes' principle, because it involves the volume of the submerged item. The formula for buoyant force reads, FB, buoyant force, is equal to fluid density. This is not the density of the solid object, it's the density of the fluid you're trying to float in this case, water. So fluid density, not iron, fluid, times the volume of the submerged item. This is again tying into the legend. The water level increased equal to the object's water volume, and so the volume here is that of the submerged item. And lastly, times the strength of gravity on this planet. The lines here are absolute value brackets indicating that you don't want the negative sign that we put on -10, you just want the 10. And all those things together will tell you the buoyant force that is currently acting on something based on its size and the density of the fluid it is currently submerged in. Is that all right so far? Okay, that's a quick sample calculation. I'm going to calculate the buoyant force on that iron weight just now. Bless you. In this case, our fluid is fresh water, which has a mass of 1,000 kilograms per meter cubed. The volume of our object is about 100 milliliters, which should be one gram per milliliter cubed. Sorry, 1 gram per milliliter. So milligrams per milliliter. It's a very, very tiny amount of meters cubed. I just converted it from milliliters to meters cubed so the units match up. And the strength of gravity on this planet is 10. So, use the formula. FB, density of the fluid, that is again the water's density, not the density of iron, is 1,000. 1, 2, 3. Oh, I did that wrong. There it is. That is the volume of the object in meters cubed. My apologies, I converted it wrong. 0.0001 meter cubed. So that is the volume we want to use. I apologize. When I'm giving you prompts on tests and homework and things, I'll try to give you the units that you need without having to convert them. This is just a weird scenario because my beaker is in milliliters. So, water density times the volume of the iron times 10 for gravity on this planet, and that should give us approximately 1 Newton up. Buoyant force always points up, because it's always opposing gravity, which always points down. So that's another golden rule you can remember. This one always points upward, unlike normal force, which can point in a bunch of weird directions depending on the surface. Buoyant force is always up. So, the buoyant force on that piece of metal is approximately 1 Newton upwards. Is that enough buoyant force to make it float? No, it is not. And that's because that weight is 1 kilogram. I will try to show where it says that. People in the front promise the people in the back that it says 1 kilogram. And 1 kilogram weighs about 10 newtons if we were to calculate the weight of that item. So gravity is 10 newtons down, buoyant force is 1 Newton up, the net force is 9 newtons down, so it sinks. But as a first buoyant force example, how's that feel? All right. Any questions before we do a little bit more practice with it? I'll make sure that all the ins and outs of it make sense before you have to use it in lab this week. All right. Got a couple more items that we'll find the buoyant force acting upon. In this example, we've got 3 cargo cubes that have fallen off of a ship into the ocean. Now, the ocean is primarily made of salt water, and so I have listed the density of salt water, which is ever so slightly denser than fresh water because it physically has more material in it. There's salt added to it, therefore there's more mass per volume of water. So if we fall into the ocean, our fluid density is going to be 1,025 kilograms per meter cubed. So that is the density of the fluid that is creating the buoyant force. The object itself does not create its own buoyant force. The fluid is what does it, and that's why we need the fluid's density. And we got 3 cubes. The first cube is 1 meter by 1 meter by 1 meter, and it has sank. It has sunk. It has sinked. Language is not my strong suit. The second cube is 2 meters by 2 meters by 2 meters. It has also sunk. And lastly, the third cube is once again 1 by 1 by 1, but it's currently floating. Half of it is sticking out of the water. So in order to use this formula properly, we need to know the volume of each of these objects. So, what is the volume of a 1 by 1 by 1 cube? One meter cubed. Very good. Volume of a cube is just length times width times height. So 1 by 1 by 1 is 1 meter cubed. And the third cube is the same. So I'll just put here V3 is also 1 by 1 by 1 meter cubed. How about the biggest cube, the one in the middle there? Instead of 1 by 1 by 1, that should be 2 by 2 by 2. Whoops. Which is not 2 meters cubed, it is 8 meters cubed. Double the dimensions in all axes, you get times 8 the amount of space taken up. That is again double in every axis. That's why it wound up being 8 times as big and not 2 times as big. So, that is the volume of each object. They've all been thrown into salt water, which we do know the density of. And what is the strength of gravity on this planet? 10 meters per second squared, but yes. So, strength of G is 10 meters per second squared. So we have everything we need to find the buoyant forces, plural, acting on each of these cubes. Setup sound all right before we start calculating? Okay. Do any of these other monitors have ink in them? Hey, nice. All right. First up, the 1 meter cubed cube that sank. Just going to keep them listed in the same order here, 1, 2, and 3. The buoyant force on the first cube, the 1 by 1 by 1 that did sink. Formula is fluid density times object volume times strength of gravity. So fluid density is 1,025 because it is salt water. Volume of object is 1 meter cubed, and the strength of gravity is 10. Therefore, the buoyant force on cube 1 is 10,250 newtons upwards, which is a lot. That is about 5 times what I weigh. Wait, that's 10 times what I weigh. For context, this red square that I've drawn around the tutoring sign is 1 meter by 1 meter. So 1 meter cubed would be this square, taking a 1 meter z-axis out from the board. 1 meter cubed is a big space. Therefore, this thing has a lot of flat surfaces for the water to create force upon, for the water pressure to create force upon. So in general, the bigger the item, the more buoyant force you're going to get, because it has more faces to act on and because it pushes more water out of the way. The bigger the item, the more water it pushes out of the way, and the harder that water is going to push back to try to reclaim its space. Water is very pushy in more ways than one. The more water you displace, the more buoyant force you end up generating. To demonstrate that point, let's find the buoyant force on the second cube, the 2 by 2 by 2 one. Buoyant force 2, it's the same water density because it's the same ocean, same fluid. What changed is that the cube takes up more space. It has a volume of 8 instead of a volume of 1. And G is still the same because you're still on the same planet. So by multiplying the volume of the cube times 8, you now have 8 times the volume. You push 8 times as much water out of the way. You generate 8 times as much buoyant force, which I believe should be 82,000 newtons. Once again, the bigger the thing, the more water you push out of the way, the more buoyant force you get. And this is one of the main reasons why boats are able to float. They take up a lot of space, they generate a lot of buoyant force. You have to build them in such a way that they take up as much space as possible in relationship to their weight. Which is why most of them are hollow. Take up a lot of space, but they weigh less because they're hollow. More buoyant force, less weight. That's why ships that are on the verge of sinking, you throw things overboard to lighten the weight. You can't really change the volume of the boat once it's built, but you can make it lighter. Anyway, increase volume, increase buoyant force, step points up. Any questions on the first two? All right, we got one more cube. That last one is also 1 by 1 by 1. It has the same total volume as the first cube. But what's different about that last one? Sorry? It is floating. And how much of it is currently above the water's surface? Half. Half exposed out of the water. If it's half exposed, its entire volume is not under the water's surface. And if its entire volume is not under the water's surface, it is not displacing as much water as it could be. showed earlier that this iron weight displaces about 100 milliliters of water, but if I am instead just holding it half out of the water, it displaces about half as much water. Only the part that is under the water's surface is physically able to displace any water. The ocean literally doesn't know and doesn't care about the part that is above the water's surface. Only the part that is under it is having any power here. So if the cube's total volume is 1 meter cubed, and that only half of it is underwater, what is the volume of displaced water that this thing generates? Half. So if half of it is underwater, you cut 1 in half and you get 0.5. Again, it is only the part under the water's surface, I'm running out of ink, that generates any buoyant force. Because if it's not under the water, it's not pushing any water out of the way. So instead of the full 1, we're only plugging in 0.5. But the fluid density and the 10 are still unchanged because it's the same ocean on the same planet. But half the volume, you get half the buoyant force, which, for some interesting reason, is enough force to keep that cube elevated. It must be made of very light material, or just isn't like if it's a cargo container, it's probably not very full. Whereas these two, probably chock full of solid metal or something. So, on the buoyant force calculating front, how does all that feel? All right. We're just going to end today looking at a couple of concepts related to this. Want to make sure you understand the ins and outs of the formula and just the floating phenomenon as well, because your lab this week is going to be about all this stuff. So make sure all this is in your notes and that you bring them this week. First concept-related question. What would happen to the buoyant forces if instead of falling into the salty ocean, you instead fell into fresh water of density 1,000 kilograms per meter cubed? Would there be more or less buoyant force? Less, very good. That's because if you plug in a smaller density, you get less buoyant force. This means it is easier to float in fluids that are more dense. That means it's technically easier to float in the ocean than it is to float in fresh water. Has anyone here been to Salt Lake? Has anyone here been to the Dead Sea? It's okay. Salt Lake is one of possibly the second saltiest body of water on Earth. And because it is so salty, because there's physically more salt dissolved into it, its density is even greater than that of ocean water, and therefore Salt Lake is pretty easy to float in. That said, it's also pretty gross, because the denser the water gets, the thicker it gets. The extreme of that is the Dead Sea, which is dead because it is even saltier than Salt Lake. It's so salty that the water is soupy, and everything in it died, and it's the easiest body of water to float in because it's so dense, but it's also really gross. It holds great religious significance, but it's not pleasant to touch. But it's easy to float in. It'd be even easier to float in something that was just twice as dense as water, but the fluids that are more dense than water are some combination of sticky or unhealthy. So, just in reference to this last part, it's easier to float in denser solutions, so that is why it's easier to float in salt water if you ignore the waves in the ocean. Does that make sense? All right. To that end, since we found all three of these buoyant forces, do you think that cube number 1 weighs more or less than this number? Actually weighs more. Cube 1 weighs more than this because it is sinking. Do Do you think cube 2 weighs more or less than this number? More, because it is sinking. Do you think cube 3, do you think cube 3 weighs more or less or equal to this number? Equals the best answer. If it is currently floating at its current depth, gravity would have to cancel out with this force to hold it in place. Now it is possible for buoyant force to be bigger than gravity, in which case you will rise until they equalize. That is again what happens when you jam the whole beach ball under the water's surface. Buoyant force is a lot bigger in that case because you've shoved a lot of beach ball underwater and the ball isn't very light. So a lot of buoyant force without a lot of weight. Buoyant force is bigger than gravity. It'll shoot upwards until they level back out and it just floats happy on the surface again. So, to reiterate, buoyant force weaker than gravity, you sink. Buoyant force greater than gravity, you rise. Buoyant force equal to gravity, you stay wherever you currently are. Which actually does cause some pieces of debris to float about 10 meters below the water's surface, because at that depth, the buoyant force is equal to their weight. So some things don't sink all the way to the bottom, they just sink until the force is equalized. But really heavy stuff will sink all the way to the bottom. The issue for humans, if you're trying to float, is whether or not enough volume of your body is underwater to push your head out of the water, because that's the part of you that breathes. That's the part that I have trouble with. There's an alternative way that you can think about whether something's going to float or not, and this is probably the version that you are more familiar with, and it's whether or not the object is more or less dense than the fluid it's trying to float in. Does that sound familiar? Yeah. If you are more dense than the fluid you're trying to float in, you will sink, and that is because your weight, your mass in your volume is bigger than the mass in the same volume of water that you've displaced. So if you are more dense, like this golf ball, you sink. If you are less dense than the fluid you're trying to float in, your mass in the same volume is less than the appropriate mass in the same volume as water. Therefore, you weigh less than the water you're trying to displace, and you float. Note that these two objects are the same volume, but because one of them is hollow and the other is filled with whatever golf balls are made of, they have different densities and therefore different weights for their volume. Therefore, the same amount of buoyant force causes different reactions based on their densities. So again, if you are trying to float, be in denser water. Questions? All right, that's it for today. Make sure to bring these notes to lab whenever that is this week for you. Let me know if you need anything, have any questions, etc. And do please have a wonderful day.